Good afternoon, everybody, and welcome to this the first video lecture on the root locus. Before that, I hope that all of you are taking care of yourself and taking care of your family also. And in the same way, you are learning from the home too. Today, I'm going to discuss on the root locus technique. This technique is used for the stability analysis. So for analyzing the stability of a system, we would use this technique. Whether the system is stable or not, that we can ascertain with the help of this root locus technique. Before that, let me introduce the meaning of the stability. Now there are two notations for the stability. One is asymptotic stability and the another is BIBO stability. This means bounded input, bounded output stability. Now, what do you mean by asymptotic stability? The meaning of asymptotic stability will be that under the absence of input, so if there is a system and if there is no input, then my output goes towards the origin. As the time progresses, the output will go towards the origin. So under the absence of input, if the output goes towards the zero, that means the system is asymptotically stable. Another notation for the stability is BIBO stability, bounded input, bounded output stability. This means that if there is a system and if I give a bounded input, then it results into a bounded output. This means the system is said to be BIBO stability. So if I give a bounded input and if it results into a bounded output, the system is said to be BIBO stable. If I give unbounded input, if it results into bounded output or unbounded output, I cannot comment on the stability. To comment on the stability, I should apply bounded inputs. So what are bounded inputs? These all are, let's say this is the signal, this is bounded by two limits, then it is a bounded signal. This is also a step input is also a bounded signal, and impulse input is also a bounded input. But you can say that a ramp signal is unbounded because as the time progresses, the signal strength goes to the infinite. So there are two notations for the stability: asymptotic stability and BIBO stability. Now, so we all of us know that the stability of a system depends upon the position of closed loop poles. So the stability of a system, I mean closed loop system, because we always wish to ascertain the stability of a closed loop system rather the open loop system. We want that a closed loop system to be stable because after all we are going to control that system via feedback. So now this is my S plane, this is the real axis, this is imaginary axis. For a system to be stable, all the poles should lie on the left hand side of S plane. So this is left hand side of S plane, this is right hand side of S plane. So for a system to be stable, all the poles should lie inside the left hand side of S plane. If any pole goes towards the right hand side of S plane, the straight away the system is unstable. So via checking, so how we can check the stability of a system? We can check the stability via knowing the position of closed loop poles. So now, how many poles are on the left hand side of S-plane, or how many poles are on the right hand side of S-plane, that we have already checked via Routh-Hurwitz stability criteria. I have already forwarded the video lectures on Routh-Hurwitz stability criteria. Hope that you have gone through that. And via preparing the Routh-Hurwitz table, so we should have a characteristic equation. This is the characteristic equations. So via knowing the coefficients of the characteristic polynomial, we can prepare the Routh-Hurwitz table, and with the help of Routh-Hurwitz table, via checking the sign of the first column element of the Routh-Hurwitz table, we can know that how many poles are on the left hand side of S-plane and how many poles are on the right hand side of S-plane. If there is any sign changes, straight away the system is unstable. So I hope and I presume that all of you have gone through this Routh-Hurwitz stability criteria. I have already posted one assignments also, which carries 4 marks. So please submit the assignments before the due date through LMS. Right. Now let us come to the root locus technique. There are 2 words in this root locus. Root here means closed loop poles. And locus is nothing but a path or a trace. So it means that it is the path of closed loop poles. Where? Inside the S-plane. Okay. So here this closed loop poles this word is very important. This closed loop poles is very important, because we would like to know the closed loop stability. Hence, we would like to trace the path of closed loop poles inside the S-plane. So whether that path is moving towards the left hand side of S-plane or towards the right hand side of S-plane, or when it is crossing the imaginary axis, these all things are very important to know about the relative stability of the system. Now, let me give you the definition of the root locus. So, root locus is the locus of all closed loop poles inside the S-plane via changing system parameters like gain k. So, root locus is the locus of all closed loop poles inside the S-plane via changing the system parameters like gain k. It means that if I change the system parameter, the position of closed loop poles is changing. Let us see an example that how if we are varying the system parameter like gain k from 0 to infinity, like gain k from 0 to infinity. So in an example, we will see that if I change this k from 0 to infinite, the position of closed loop poles is changing. Now we would like to know, or we would like to trace all these positions of closed loop poles inside the S-plane when the system parameter like gain k is changing. Let us see with this example. So I have an open loop system. Of course, this is open loop system like this. Let's say that is k upon s plus 1 into s plus 2. This is open loop system. It means that s is equal to -1 and s is equal to -2 are open loop poles, and there are no zeros in this system. Now, I will make the system closed loop to get closed loop poles. So 1 plus g of s h of s, this is the characteristic equation. The roots of the characteristic equation are the closed loop poles. So if I can able to calculate this characteristic equation, then 1 plus g of s h of s is nothing but k upon s plus 1 into s plus 2. This implies that s plus 1 into s plus 2 plus k, which is equal to 0. So this is the characteristic equation. Now here, if I can simplify this polynomial. I can get the roots of this polynomial, and these roots of this polynomial are the functions of k. These roots of this polynomial are the closed loop poles. So roots of characteristic equation are closed loop poles. So now I will focus on this characteristic equation. So let me write this characteristic equation here. That is s plus 1 into s plus 2 plus k is equal to 0. This is characteristic equation. The solution of the characteristic equation are the roots, and these roots are known as closed loop poles, and they are functions of k. Which means that the closed loop poles depends upon this k. Now I want to vary this k from 0 to infinite. Of course, there are two poles here. So pole P1, pole P2, and let's say this k. If I prepare a table like this. Now let me put k is equal to 0, because I need to vary the k from 0 to infinite. So I put k is equal to 0. If I put k is equal to 0, the closed loop poles are s is equal to -1 and s is equal to -2. Similarly, I can put k is equal to 1. If I put k is equal to 1, I will get some other roots. I can find that also via solving a quadratic polynomial. So there will be another root, another closed loop pole. K is equal to 2, another root. K is equal to 3, another root. Similarly, I can go up to infinite. I will get another poles. So a pole P1 is changing its position from -1 to this, to this, to this, and this. Another pole P2 is changing its position from -2 to this, 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 and this. So a closed loop pole P1 is moving from -1 to this way. A closed loop pole P2 is moving from -2 to this way, and so on. So this is the path covered by pole P1 from -1 to this, and a path covered from s is equal to -2 to this. This is known as the root locus. A path traced by both the poles P1 and P2 inside the S plane when a parameter k is changing from 0 to infinite. In this way, we can sketch the root locus. But this example was very simple because there are only two poles, and I need to compute these poles for every value of k from 0 to infinite. So it is a cumbersome task. It is a computationally intensive, though I need to solve a quadratic equation to get P1 and P2 for different values of k. But this situation would be more difficult if there are 3 number of poles or 4 number of poles. Then I need to solve a polynomial of 4th order. This is extensively difficult. But root locus will give you a technique to get this path easily. So let us understand now. So I'm taking one example of root locus. For example, if this is my S plane, this is the origin of S plane, and let's say this is the root locus. This is the path, let's say. It means that the entire path, this path would be for k is equal to 0 to infinite. So for any value of k, the root locus is staying inside the left hand side of S plane. It means that for any value of k, the system will be remaining stable. If let's say this is the root locus, then it means that for this value of k, the system is stable, and for this value of k, the system is unstable. Okay. So once the root locus is sketched, I can check the stability of the system. I can check for which value of k the system is stable, for which value of k the system is unstable. For the time being, I am keeping this lecture here closed, and I will back to lecture number 2. Now in the next lecture, we will going to see that how to sketch the root locus. So there is a procedure, there is a standard procedure. If we follow that standard procedure, then we can sketch the root locus. Thank you.